And we're live. Excellent. Oh, goodness gracious. What a morning it has been. Last day before a 4-day weekend in which New Jerseyans are told not to travel or have gatherings of more than 10 people. It is amazing. But anyway, I'm having an interesting morning. Interesting morning in regards to the quality of my live stream. For some reason, I have two. Okay, I have two cameras going at once. I have the camera going here, and I have the camera going here. And the camera going here is from my cell phone. I have an app that projects a webcam feed directly to the Wi-Fi. And that Wi-Fi is fed back into my computer, which is what you see before you hear. But the webcam that you see right there, that is hardwired directly into the computer. And the computer is hardwired directly into the internet. The problem I was having this morning, which I'm just going to give you the heads up before, or if it happens, I'm going to say if because I'm really hopeful, but if it happens, then what would end up happening is this screen down below might end up freezing. And if this screen below ends up freezing, what is this? There we go. If this screen below ends up freezing, then the webcam would actually still work, which is really weird to say the least. I don't know. It's one of those things. But I can still finish up whatever lesson I'm trying to do. So we'll figure it out. Anyway. Okay. A couple of reminders before we get started. For those of you that are here and those of you that are watching this on a playback. You do have an EdgeElastic assessment due for me today. I can see that a handful have already gotten it done and submitted it. Please make sure that you are actually clicking submit on that thing so that I can adjust the grade accordingly. It looks like so far 5 out of 22 have submitted it. There is one question on that assessment that I have to manually grade. There is one question that I have to manually grade. It's the one where you had to explain how you would go, the process you would go about, and I'll do that today. But of course, I want to give people until 2 o'clock to kind of do it. I see you there. Yeah, I see all you guys in that chat. Look at you, being all responsible and showing up to class. Regardless of that assessment being due today, next week, I should be back in my classroom. You guys would still be quarantined for next week, but I would be back in my classroom next week, live streaming and doing all that fun stuff. I'm going to try and figure out how to get OBS Studio hooked up to my computer at school because apparently it won't let. I don't have administrator access to those things, but I like OBS Studio because with OBS Studio, with OBS Studio, I can do stuff like this, and you can see me, live like that, or, I could go to a website, and I could kind of go around a website or show a video or something like that, or I could do my top down, and you could actually see what I'm writing in real time. But that's what OBS Studio allows me to do. I'm just saying. Anyway, so here's what I would like to do. I'm not going to keep you for the full time. Technically, I have you from 9:28 to 10:28. I'm not going to keep you for the whole time, but I'm going to get you some information. So if you do not already have them out, I'm going to need those notebooks out and open. Today is the 25th, and this is an intro to polynomial graphing. Now, we generally know how to graph things. If I gave you a linear equation, clearly you'd be able to figure out how to graph the linear equation. If I gave you a quadratic perhaps you would figure out what the vertex is and be able to determine approximately what that would look like. For a polynomial, it gets a little trickier. For a higher level polynomial. Technically, linear and quadratic are polynomials, but I want to go higher level with the examples that I have for you today. And in order to graph them properly, we need to have proper points. Proper points in terms of the zeros of the function, and in terms of end behavior. I haven't talked about end behavior, but I really need to talk about end behavior of graphs. And when I'm talking about the end behavior of graphs, I am literally talking about how those graphs are moving to the left and to the right. How are they moving in terms of up and down situation? But, again, we'll deal with that when we get there. Let's talk about end behavior. There are technically 4 types of end behavior when it comes to polynomials. 4 types, very basic types. And I'm going to give them to you. I'll give 2 on this page, and then I'll give 2 on the next page, because I want to spread out and write some extra information in when I get there. So one type of end behavior is when both the left and the right ends of that graph are going upward as you move to the far right and to the far left. Typically, you would see that in a quadratic, for example, that had a positive leading term. Yay. You could also see that end behavior doing something like this. Now, there's a reason why I left the middle blank. We don't know what the middle is going to look like. We don't know what the middle is going to look like until we actually get into the details of factoring that thing out and determining what the heck is going on. It could be a quadratic. It could be a 4th degree, a 6th degree. I don't know. It might have a number of different turns going on there, turning points. I don't know. But this is what the first 2 forms could be. Now, in order to identify them, there's a basic term in order to figure this out. If you have end behavior that resembles these 2 examples, these are 2 separate examples, mind you. If you have an end behavior that represents these 2 examples, then the degree of both of those is going to be even. The degree is going to be even. Absolutely, yes. Now we'll deal with odd degrees in a few moments, but the degree is definitely going to be even. Oh, I see you guys in the chat. I see you, Tristan. If you have that kind of question, just email me. Email me, because Anyway, but I can discuss those issues after the fact. I'm just gonna continue. Well, because this lesson is for everyone. If the degree is even, then yes, you're going to have your end behavior go in the same direction. Both the left and the right end will either both go up or they will both go down. What determines whether or not it goes up or it goes down as to what is the leading coefficient. Now, we've talked about coefficients before, but the leading coefficient I'm going to define for you in a little bit. But if the leading coefficient is positive, then you are going to have end behavior, in this case, that both go up. And in this case, if the leading coefficient is negative, then both end behaviors are going to go down. Some examples of this. I'll show you just visually on the calculator right here, so you can kind of see this along with me. Something very basic, an x squared plus x plus 1. The degree is 2. The leading coefficient is the number that is in front of the variable with the largest exponent. It's the coefficient that is paired with the degree of the polynomial. In this case, it's a positive one, so you can see the end behavior. Now again, it doesn't matter what they do in the middle. It doesn't matter what it does in the middle. Look what it's doing to the left and to the right. both going up. Or I could change this to be a negative. It's still a degree of 2, and you can see clearly, again, doesn't matter what it does in the middle, but you can see clearly that both are heading downward. These are two examples of even degrees. I could change it to like an x to the, I don't know, to the 6th power. I'm going to make it a 6th degree polynomial. I'm going to throw in a bunch of stuff afterwards just for the fun of it, just to kind of see what happens here. I don't know. But it's a 6th degree polynomial, which means that it's an even degree, and that's a 1 in front of the term with the degree. So it's positive. Let's look at the graph. Doesn't matter what it does in the middle. Look at the end behavior. To the left it's going up, to the right it's going up. Now there is a certain terminology to it, basically, which is really weird, that the way they write this thing out. This terminology for the end behavior. I'm not really a huge fan of it, but unfortunately, when it comes to assessments that the Algebra 2 teachers would assign, a lot of them are fans of it. So it doesn't really matter if I'm not a fan of it, if they're going to throw that kind of thing on their assessments. And like the midterm, for example, I need to put this on my in my notes as well. But basically, for this type of end behavior, as x approaches infinity, it's a very strange thing. But basically, as x approaches infinity, that means that literally translates to, as you're moving to the right, the function's moving up. That's what that sentence, literally that sentence, translates to become. As your x is approaching a positive infinity, your f of x is also approaching positive infinity. It literally translates, as the graph moves to the right, it also goes up. It's a terrible notation, but I need you to be aware of that because they may throw something like that at you on the midterm, which is created by all of the Algebra 2 teachers. I would also have to talk about the left. As x approaches negative infinity, meaning as you move to the left, what is the graph doing? It's still going up. It's still going up in this particular example. So it's also headed towards infinity. Again, a terrible type of example, but basically this describes end behavior. They may throw this kind of notation at you and be like, well, what's the graph? What might the graph look like? And you'd be like, okay, let me think about this. And then you kind of go through that process of determining, okay, as it's moving to the right, the graph is moving up. And as it's going to the left, the graph is going up. Which means, if they're both going up, it's an even degree, and it's a positive leading coefficient. That's how you would interpret that notation for end behavior. I could do the same thing here. As x approaches infinity, meaning as you move to the right, f of x is actually headed down for this example, towards negative infinity. Same thing for the left side, the left end behavior, as they put it. As x approaches negative infinity, meaning as x goes to the left, the function is headed down. Left end behavior. Again, it's a terrible notation. I am not a fan of this notation the way that they do it. But again, it's something that the other teachers like, and they most likely will try to put it on the midterm because we collectively put the midterm together on Linkit. And I just want you guys to be aware of that. So, yeah. Now, I did say there were 4 types of end behavior. These 2 types of end behavior that you see in front of you right now are both when you have an even degree, a 2nd degree, a 4th degree, a 6th degree polynomial. Either your both ends are headed up or both ends are headed down. Now, obviously, there's an odd type of end behavior. There's an odd type of end behavior, and that odd type of end behavior, there are two instances, which I'm going to display for you here. An odd type of end behavior where clearly one's headed up, one's headed down, or it looks like that. Now this is an odd degree. The degree in this case is going to be odd. A first degree, a third degree, a fifth degree. I'm going to write that here as well. The degree is odd. Think about a linear equation. A linear equation is a first degree polynomial, meaning it's odd, but then what does it look like? It's either sloping upward or it's sloping downward. But it represents this end behavior. Again, I left the blanks in the middle because we don't know what's going to happen in the middle. It could be doing all sorts of wavy turns in the middle. The leading coefficient, however, the leading coefficient, which again is the number that is with the degree of the polynomial, the coefficient in front of the degree of the polynomial, in this case, it would be positive because it's sloping upward. And in this case, it would be negative because it's sloping downward. You can always determine what the leading coefficient is, what the degree is, based on the end behavior of the graph. Now I do have to give you that other notation that I'm not a fan of. But again, I need you to be aware as to how to do it. I'm going to maintain doing it that way. So we have to talk about the left side and the right side before we get into some examples. So, as x goes to the right, which means, as x approaches infinity, f of x, for this example, is also going towards infinity. There are certain things in mathematics that I'm like, yeah, I understand how to do that, but I don't, see the point in it. I really don't see the point in it. But again, it's one of those things where it's like, they're going to throw that on an assessment, and I don't want you to get it wrong. So I'm going to maintain teaching it. But that's the right end behavior. As you go to the right, it's going up. As x goes to the left, approaches negative infinity, the graph clearly is going down. So it's also approaching negative infinity. You can think of infinity and negative infinity. They're not numbers. They're actually concepts, but that's why I say it's approaching. It'll never actually get there. Kelsey, which specific part? Was it the end behavior part? Was it the odd degree part? I want to be very clear about what your question is, because there is a little bit of a delay between what I said and me reading the comment. I'll give you a moment to type that in, obviously, because there probably was a delay in me saying that and you hearing that. End behavior. Okay. I'll do if you have a more specific question, please type that in, but I'm going to just do a general statement on end behavior, hopefully clarifying what you just said, or what you just asked. End behavior, quite literally, is how the graph behaves at the far left end and the far right end. The graph in the middle might do all sorts of weird things. For example, I'm just going to throw in a cubic here. X cubed minus x squared, plus 2x minus 1. Again, I'm just throwing in something silly. Wow. Nah, I don't like that. I want one that actually is going to work the way that I want it to work. It's a little better, but let me put back in the minus, and let me put in minus 5 right there. There we go. Perfect. Perfect. The graph in the middle is going to do all sorts of crazy things. In the middle, this graph actually crossed the x-axis 3 times. But that's not the point of end behavior. End behavior is how the graph behaves to the left and to the right at its ends. So for example, if I were to keep moving to the right on this graph, what direction is it headed, up or down? And it's headed up. As I move to the right, at the same time the graph is moving up. And you can see that in its, there goes my marker, in its end behavior, how it behaves. Now the way that I write that is like this. As the graph goes to the right, the function is going up, is how they typically write that kind of information. And you can see it here in the actual formula. Let me go back here to y equals. It's a third degree polynomial, meaning that it is an odd degree. And you can see that odd degree right there. And the leading coefficient is a 1. Thus, it's a positive leading coefficient. So the end behavior is going to resemble this. But the notation, the way that you would typically write it, is like this. As the graph goes to the left, look where I'm pointing, as the graph goes to the left, as it approaches negative infinity, the graph is going down, meaning the function is also approaching negative infinity. It's a very strange thing. Now, check this out. I'm going to change one thing, and I'm going to finish this last example along with it. I'm going to throw a negative in as the leading coefficient. I'm going to throw a -1 in as the leading coefficient, just for fun. Graph. Ooh, I don't like that. I mean, I like that, but I don't like that. I want it to look a certain way. So I'm going to have it look like this. There, I fixed it. The leading coefficient is negative. Leading coefficient is negative. It's a -1, meaning right here you can see leading coefficient is negative. It's an odd degree. You can see because it's a third degree polynomial, meaning that, well, the end behavior should resemble this. And it does. Doesn't matter what happens in the middle. Look what I just covered up what happened in the middle. I covered it up. But to the left, it's going up, and to the right, it's going down. We'll figure out what happens in the middle in a few moments. But the way that we typically write that is like this. As x approaches infinity, meaning as you move to the right, the function is headed down, meaning it's going towards negative infinity. That's the right end behavior. As x goes to the left, as I'm heading this way, the graph clearly is going up, so the function heads towards infinity. The first statement for the x describes what direction you're headed, left or right, and the second statement, f of x, describes where you're headed, up or down. That's what that thing does. Now, I have an example that I would like to graph with you guys. I have an example, a few examples actually, that I would like to graph with you guys, and there's going to be a little bit of legwork in order to get those things done correctly. The legwork that I'm referring to is determining the end behavior, number one. Number two, determining where it crosses the x-axis, because I do have a few examples that I would like to try. And then we're actually going to try and graph this thing out. We're going to try and graph it out without looking at the actual graph. Now it's like, Ms. Mark, we have graphing calculators. I know you do. I know you have graphing calculators. But what's going to end up happening on Linkit? What's going to end up happening on Linkit is it's not just going to be a simple, hey, graph this. It's going to be something more along the lines of, here's what the graph looks like, tell me some of the characteristics, and write the proper notation, or something along those lines. Or, here's some of the attributes or characteristics of the graph, can you tell me all this other stuff now? We need to get into that. Let me show you what I mean. I appreciate you guys all saying hi. You don't have to say hi to me, but I do appreciate it. It's nice. Makes me feel all warm inside. So, whatever. Okay, let's try this example. And then we're going to talk about some of the things behind it. So I'm just going to graph a random example. Okay, just a random example. And we're going to talk about some of the details that we can go along with it. So draw this to the best of your ability. Draw that example to the best of your ability. It's a ridiculous example, I know. But there's a purpose to what I'm showing you here. There is an absolute purpose to what I'm showing you here. Now, there are certain things that I can ask you about this graph. There are certain things that I can ask you about this graph. I don't care what the numbers are. I don't care exactly where it crosses the x-axis. That's not what I'm interested in. What I'm actually interested in is, well, okay, first, can you tell me anything about the degree of this polynomial? Well, I can tell you that the degree of this polynomial is definitely going to be odd. It's definitely an odd polynomial because of the end behavior. One end behavior is headed up, the other end behavior is headed down. It's definitely odd because they are going in, wait for it. You ready? I'm going to tell you the best joke ever. They're going in opposite directions. Opposite directions. I'm very proud of myself. I just want you guys to know that I'm very proud of myself. Anyway, back to this. I can also tell you something about the leading coefficient. Because of the way that the end behavior is structured with the left side to the right side, look at the end behavior and notice the type of slope that I am making between those two ends. I can tell you that the leading coefficient's definitely positive. Definitely positive. I could tell you a lot more too. I can tell you how many turns this graph had. And by determining the number of turns, I can make another more detailed statement. Now, there's a turn here. Remember, a turning point is a change in vertical direction. A change in vertical direction. There's a turn here. 1, 2, 3, 4. There are 4 turns. Now, I go back to the definition that we wrote down in a previous class period. Actually, it was Monday. On Monday, we wrote down the definition that if the degree is n, then the graph will have at most n minus 1 turns. Well, this one has 4 turns, meaning the translation of that means, hold on, let me actually write down the statement. This means a degree of at least 5. It's a degree of at least 5. Because if the degree were 5, then it would have at most 4 turns. It would have at most 4 turns. Also, look how many x-intercepts it has. It has 1, 2, 3, 4, 5 x-intercepts. According to the degree of a polynomial and x-intercepts, the zeros that we talked about, the real solutions, if the degree of the polynomial is n, then it would have at most n real solutions. It looks like this is a 5th degree polynomial. I mean, it could be a 7th. It could be a 9th. I don't know. But I can tell you all of this stuff solely based on the end behavior of the graph and how the graph actually looks. I could also describe the end behavior using the notation that we talked about, because again, this is something that you may have to end up doing. But I can also describe the end behavior. Hold on, let me actually do this. Real solutions is also 5. I just wanted to write that in there for the sake of argument. But the end behavior of this graph, as x goes to the right, as x approaches infinity, the function is going up, which you can see right there. It's clearly going up as you move to the right. as x goes to the left, as it goes to the left, the function is going down. That's what that notation means. Negative infinity would either be to the left and down. Positive infinity would be to the right and up. But again, you'd have to describe it in two ways. You're describing a left-right behavior, and you're describing an up-down behavior. That's what this thing is doing. I love it so much. Let's try to actually graph one. Let's try to graph an actual example. Let's see what this is going to look like. This is going to be amazing. Amazing for me, not for you, probably. Just flat out amazing for me. Let's see what we got here. Come on, little paper. Here we go. Okay, let me write down this example. No, I don't like that example. I like that example. Perfect. Okay. Example. F of x equals x to the fourth power plus x to the third power minus 7x to the second power minus x plus 6. I'm just double checking to make sure that it's written exactly the way that I need it to. And it is. Excellent. So now, what do we know about this graph? We know many things without even looking at the graph, because I'm not going to look at the graph here. I am not going to look at the graph there. I may end up using the table of values in a little bit. You'll see that with the table of values, but the table of values is going to be like a last resort with this problem. But what do I know? I know that this graph would have, or the degree is 4, meaning at most 4 real solutions. It would have at most 3 turning points. I know that the end behavior, actually no, I need to identify the leading coefficient too. The leading coefficient of this problem is a 1. It's a 1 because of that 1 right there, which means that the end behavior should resemble something like this, which I'm going to write the proper notation for it in a little bit. I just need to identify some of these things going on here. I know all of this information now. The degree is 4, the leading coefficient is 1. The end behavior should look like that little sketch. At most, it would have 4 real solutions. At most, it would have 3 turning points, according to the definitions that I gave you on Monday. Man, I really wish I knew what those solutions were. If only I knew exactly where those solutions would occur. I mean, it would be kind of nice to be able to kind of like, know exactly where this thing is. Because you're not sketching it. You are not going to sketch what this graph looks like. You are going to graph it appropriately and be able to tell me the appropriate information. I look at the graph. Oh, what did I type in? Oh, I didn't put in the proper square. I put in a 2 right there. Square. There we go. That should work now. There it is. Look at that wonderful graph. Something funky is going on down there, but we'll deal with that in a minute. It looks like, if you took a look at your graph, it looks like it does indeed cross 4 times. And down here, I don't know what's going on down there, but it looks like it does a turning point down there. It does a turning point up top in the middle, and it does a little turning point right there as well. That's 3 turning points. And the end behavior. Look at that end behavior. To the left and to the right, they're both going up. Interesting. We need to confirm, we need to prove, we need to show that those real solutions are what they say they are. I guess it's time for some synthetic division. Let's try some synthetic here. I got a 1, a 1, a -7, a -1, and a 6 for the coefficients in order. Largest exponent to smallest exponent. This number right here is why my leading coefficient is a 1. According to the graph, it doesn't really matter which one I start with. Let's start with, I think, +2? Yeah, it looks like +2. +2 could work. Let's try +2. Okay. 1, 2, add, multiply, add, multiply, add, multiply, add. It worked. It totally worked. Now keep in mind, the resulting equation is a cubic equation. It's a third-degree equation because look, I got a remainder, a constant, an x squared, and an x cubed. But that's not the point. I need to confirm the rest of these as well. So I'm actually going to do another synthetic, but using those resulting numbers, not the remainder. Don't use the remainder. But I got to try a different 0 here. Let's try +1. I'll try +1. 1, multiply, add, multiply, add, multiply, add. It worked. Now at this point, you have options. At this point, you have options. Your options could be to continue with synthetic. You could continue with synthetic if you wanted to, because you have two other zeros that you could visually identify. Or remainder, constant, x squared, you do have a quadratic here. I'm going to do the quadratic. Again, it doesn't matter what I do here, but I'm going to do the quadratic. This is an x squared plus 4x plus 3. I can factor that. I can factor that into x plus 3 and x plus 1, which would produce solutions of -3 and -1. Once I solve that, setting it equal to 0, of course. I'll actually do that here. Here we go. What the heck have I done? What the heck have I done here? Well, what I've done so far is this. I have proven that the real solutions of this problem are x equals 2, x equals 1, x equals -3, and x equals -1. I have proven that. This has been proven. Yay. I proved the 2 up here, I proved the 1 down here, and I proved the other 2 by taking that quadratic and whittling it apart. Nice. I've also proven the factors. I've also proven the factors of x minus 2, x minus 1, and these two over here, x plus 3 and x plus 1. I have proven that as well. All from this one equation. I would like to graph this thing. I would like to graph this thing. I need another piece of paper. In order to graph this thing properly, I have almost just enough information. I almost have just enough information. Okay. Let's create a little XY plane action going on here. I'm going to you don't have to do this, but I'm going to rewrite my equation just so I can see what that equation is, so I don't have to keep referring to the other page. But I have proven so much stuff so far. We knew at most how many real solutions, how many turning points it could have. We know what the end behavior is. We know what the real solutions are. We know what the factors are. There's only 2 things left to do. I want to graph this thing properly. Before that, I need a proper table of values. I need a proper table of values. Now here's the thing. I know what the real solutions are. And in fact, if you go to the calculator real quick, second graph will take you to a proper table of values. Now this table of values won't tell you everything. This table of values will not tell you everything. But if you go back right here, look at that right there. Oh, look at that. Look at that amazingness right there. There's that first 0 at -3. I'm going to write down some information. I'm going to write down -490. I'm going to write down -3 0. I'm going to write down -2 -12. I am going to write down -1 0 0 6, which is the y-intercept. I'm going to write down 1 0 2 0 3 and 48. Yeah, that's as far as I'm going to go. For the examples that I'm going to give you, pretty much, I mean, once you get to like some larger double-digit numbers, once you reach numbers that reflect the end behavior, you pretty much don't have to go any farther than that. I'm not actually going to plot -490. I'm not actually going to plot that. I'm not going to plot 348. I'm not going to plot that either. I'm just having them in my table of values as a reference. Let's put some of these points down. There's -3 0. There's -1 0. There's 0, 6. Now I'm going to have to do -2, -12, so 6, 7, 8, 9, 10, 11, 12. -2, -12. There's that one right there. I'll answer your question in one moment. I just want to finish plotting these points. 1, 0. 2, 0. And I'm not going to plot 348. Okay. The question was, what exactly was that you wrote in the XY table of values? What I wrote, you mean? Well, in my y equals key is the equation that we've been dealing with. That's the equation for this entire example. And in order to get an accurate graph, if I hit second graph would take me to that table of values. Now, unfortunately, you guys might not be able to see it as clearly as I can see it right here. But what I did was I went back in my table of values until I reached some of these terrible numbers up here. You can see that they're like 3-digit numbers up here, 4-digit numbers up here. I'm not writing down those 4-digit numbers or 3-digit numbers. I went to like the first big number, which in this case was like 90. And I wrote it down, but I'm not actually going to plot that -490. I'm not going to plot it. And then I got -3 0. -2, -12. I'm just literally, I'm copying these down, but you know, I'm going to show you something in a minute. -1 0, 0 6, which as I said, 0 6 was the y-intercept. 1, 0, 2, 0, which we already knew those from before, and 348, which I'm not going to plot 3, 48. I'm not going to plot that whatsoever. If you notice, we already knew most of these right here. Look, -3 0, we knew that one. That was an x-intercept. We knew -1 0. We knew 1 0, we knew 2 0. We knew all of those numbers based on the work that we did. The rest of them came from the table of values. Now, there's a huge mistake that a lot of people end up making when they get to this point right here. There's a huge mistake that a lot of people make. I've seen people do this where they've been like, okay, connect the dots, connect the dots, connect the dots, connect the dots. It's not a game of connect the dots. You have to go through the points with a smooth curve from left to right. I don't care how far up and far down these points are. You have to go through these points with a smooth curve from left to right and properly show the end behavior, which I'm going to do that with you. If I'm going to go through left to right, I'm going to do something like this. Now again, I'm going to be very careful with this. I'm going to be very careful with this. I'm drawing this in permanent marker. You should hopefully be drawing this in pencil. look, this graph from left to right is going to have a certain number of turning points that we saw. Now, I need you to be very careful right here, because what a lot of people incorrectly do is they create just like a horizontal line between those two. But again, looking at that graph, that doesn't look like a horizontal line to me. That's a smooth curve, which means it's going to dip and then go back up. Here's the other thing that I've seen. I've seen people leave it like this. This is not correct. You cannot leave it like this. We talked about the end behavior, what the graph does to the far left and the far right. Now, if you notice, I did not plot negative 490. I didn't plot that because I can't fit it. But negative 490 would be like way up here. It'd be way up there. And 3,48 would be way up here. There's a proper graph right there. That is a proper graph of this equation. Now let me just write in my end behavior here. As x goes to the right, f of x is going up. And as x goes to the left, the function is also going up. Look at all that we've done for this problem. This would be an amazing, huge, multi-step problem that you could get done for me on an assessment. It is phenomenal. Let me show you what I mean. Again, I'm just going to recap everything that we just did. First, I gave you that equation. From that equation, you could identify the degree of the polynomial, the largest exponent, the leading coefficient, the coefficient that's with the largest exponent. Because of the degree, based on the definitions that we wrote down last time, this graph has at most 4 real solutions and at most 3 turning points. And because of the degree and the leading coefficient, we could determine a little sketch as to what the end behavior should look like. Okay, so we did the same thing we normally do. I looked at the graph of the polynomial. I typed in the polynomial into the y equals key. I graphed it just to see what it would look like. And it should look something like this. But again, don't do that, because this thing does dip down below and come back up. If you left that as what you saw on the screen, I would not be happy. But I can visually identify, it's got a few zeros I could divide out. So I did a synthetic division. It looked like positive 2, and I proved it right here. I proved it. I took the resulting numbers, and I did it again with another 0 that I identified. It doesn't matter what order you take them out in. But what was originally a 4th degree polynomial, after I divided out 2 of the zeros of the function, resulted in a quadratic. Remainder constant x squared. The resulting quadratic, now I could totally keep going with synthetic, or I could do the quad formula, or you can factor them. Factoring it resulted in these 2 zeros. These 2 zeros and these 2 zeros were indeed the 4 x-intercepts. They were the 4 real solutions of the graph. And if you have the real solutions of the graph, you also have the factors. I lined them up vertically just as a comparison so you could see what the factor was compared to the solution, or the zeros. There we go. So then, using all of that information, I needed to graph it. I plotted a few of those zeros. But I'm also going to utilize my graphing calculator, second graph, to get an accurate table of values. You're going to write down that table of values, as I did right here. Now, you don't have to write down a million numbers As you can see, once I get past negative 490, I'm not even going to plot negative 490, but I'm going to write that down simply because, well, that's where the end behavior is headed. That is where the end behavior is headed. It's headed up towards positive infinity, as you can see right there. So I wrote down negative 490, but then I wrote down everything in between until I got to 3,48. Because after 348, oh man, yeah, I knew the end behavior was going to do something like that. I knew that. So I stopped at 348. Once I had all of those points, I plotted them where they should go. I knew what the end behavior was supposed to look like. I created a smooth curve between them. Just because these two line up horizontally doesn't mean that you're going to have a horizontal line. There's not going to be any horizontal lines here. It's all going to be smooth curves, as you can see on the example of the graph. And I filled in that end behavior the way it should look and wrote down the proper notation for that end behavior. This is an all-encompassing problem. This has all been one problem over the course of the last 20 minutes. I love it. Now, will a problem like this take you 20 minutes? Maybe at first. But eventually, no, it won't. I took my time with this. I purposefully took my time with this problem because I wanted you to see all the steps that were involved. Okay. Now, this was an introduction to the graphing that I have for you. This was just an introduction to the graphing that I have for you. Obviously, this is going to continue through next week. This is definitely going to continue through next week. So, you have an edge elastic assessment due from me. If you did not get that edge elastic assessment done, because I can see who has and has not submitted it, if you have not got done that edge elastic assessment, you need to get done that edge elastic assessment. By all means, please do so. I'm actually loading it right now to see how many people have done it. Come on, dashboard. There we go. Period 3B. Yeah, the internet's acting slow right now. That's okay. It's perfectly fine. Fun stuff. He's going to go get a physical. Everyone be happy for him. But keep in mind, whatever you end up getting on that assessment, I do have to manually grade one of the questions. So, if you would, the class period is coming to an end. Obviously, you do have fourth period, so please make sure you're going to your fourth period classes. But if you do not have a fourth period class, or if you're going to go get a physical, please, by all means, make sure you are getting my assessment done. I'm going to sign off in a minute. I'm just allowing that delay to occur if people do have questions for me if need be. Otherwise, I will officially end class for the day, and I will hopefully see you guys back in my classroom. I'm sorry, let me rephrase. You will see me back in my classroom, but I will not see you back in my classroom for another couple weeks. So, have a happy Thanksgiving for your less than 10 people, and I will see you guys another time.